So in today's video, we're going to go ahead and continue our study of antiderivatives and their correlation to indefinite integrals. And so in the previous video, I actually took a look at what the indefinite integral even is, and we essentially determined the fact that the indefinite integral gives a sort of general form of the antiderivative of a function, right? And so in this video, we're going to go ahead and make that a little bit more concrete because that seems rather abstract by doing a couple of different examples. And so given the antiderivatives, find the integrands. And so here we're given the indefinite integral of lowercase f of x dx, and that's equal to 4 tangent of 2x plus 1 plus c. And just a little bit of a review, we add this plus c over here as the constant of integration because when we differentiate this function, then that plus c will disappear, and we will be left with the derivative of the antiderivative. So we'll essentially be left with this integrand right over here. And actually, that is the process of finding the integrand. So what we can do is we can apply the derivative operator to both sides, and you can kind of think of the derivative and the integral canceling out. So the derivative with respect to x, the derivative with respect to x, right? You can kind of think of these two canceling out, right? You're taking the derivative of the antiderivative of a function, so you'll just be left with that function. And then here we'll be left with f of x, lowercase f of x, is equal to the derivative with respect to x of 4 tangent of 2x plus 1, right? If you want to quickly use the chain rule, you'll end up with 8 secant squared of 2x plus 1. And then this plus c right over here, keep in mind, this c is just a real number, so this will go to 0. And so this right over here is the integrand. So another way to write this is just to say that the indefinite integral of 8 secant squared of x, or secant squared of 2x plus 1 rather, dx is equal to 4 tangent of 2x plus 1 plus c. And this makes sense, right? Because this right over here is the derivative of this expression, of this function right over here. And this function on the right-hand side is the antiderivative of the integrand. And so I hope that kind of makes this a little bit more concrete. And then another example, we have the indefinite integral of g of t dt, right? And it's equal to the natural log of t cubed minus 3t squared plus 1 plus c. And again, what we can do is we can just apply the derivative with respect to t in this case, because that's the new independent variable that we're considering of both sides of this expression. And then again, you can kind of think of these two canceling out. You'll be left with g of t is equal to, again, this plus c will go to 0. The derivative of the natural log of t cubed minus 3t squared plus 1. Again, you can quickly use the chain rule in your head, and you should end up with 3t squared minus 6t over t cubed minus 3t squared plus 1. And so essentially, if we were to integrate this function right over here, if we were to integrate this rational function, i.e. if we were to take the antiderivative of this function, then we should end up with this natural log of t cubed minus 3t squared plus 1 plus c. Never forget that plus c, because that does make a difference when you are taking antiderivatives. And then next up over here, what is the definite integral of negative 10 cosine of 5x minus 7 plus 1 dx, right? And so here we're given the actual integrand, and we're trying to find what the antiderivative of this function right over here, of this integrand, actually is. And so here we're given 3 different options. And the way that we can approach this is we can think that each of these functions, or for one of these functions at least, since we have to pick one of them, the derivative of the function is going to actually be this integrand right over here, right? Because this, we're saying that when we take the indefinite integral of, this function, we can call this function lowercase f of x. When we integrate this function, then we are taking the antiderivative of it, which means that when we take the derivative of this integral, we should just end up with lowercase f of x, right? And so if this, for example, if this expression right over here is actually the integral of f of x dx, then when we take the derivative of this expression, we should end up with f of x. So let's actually go ahead and try to see if that's even the case. So if we take the derivative with respect to x of this expression right over here, again, plus c will go to 0. And then if we quickly use the chain rule, we'll get negative 10 cosine of 10x minus 7, and then plus 1. And so this right over here doesn't work. We do have that plus 1, we do have the negative 10 in the cosine, but this argument right over here is incorrect. So we know that this is not actually the correct answer. And then again, we can apply the derivative to this expression right over here to see if that works. Okay. Again, plus c will go to 0 because it's just a constant. And then we can apply the chain rule. We'll end up with what? We'll end up with negative 10 sine of 5x minus 7 plus 1. Again, we have the negative 10, we have the correct argument in the plus 1, but we're taking the sine of the function, which is not what we want. We want cosine. So this can go ahead and disappear. And then finally, process of elimination. This one should work, but let's go ahead and actually verify that. We take the derivative, this plus c goes to 0. And then again, you quickly use the chain rule in your head, and you should end up with negative 10 cosine of 5x minus 7 plus 1. And so we know that this right over here is the correct expression. So we can say, if we want to, write this down, we can say that this is going to be equal to negative 2 sine of 5x minus 7 plus x, and then of course we can't forget the plus c, and that would be your final answer.